recording. I show the chat, and off we go. So, we had discussed all this, computing the ACF, and now we are in chapter 4 about forecasting a stationary process. Where are my notes? Here, there. Okay, so everybody's comfortable, everybody sees well. Okay, so this is a rather technical chapter again, about things that are again all pre-implemented in R. It's about how you can predict. So the idea is you have your time series, it's moving with time, and you suppose that as time passes you're gathering information, and then now you're at this step here, you're at step n, you have all the information up to time n, and you're wondering how can I predict the value at n plus 1, how can I predict the value at n plus 2, and so on. And you would like to have a prediction about the future of your process built upon the observations from x1 to xn. And well, basically we know the answer to this. We know that the optimal prediction of xn plus L, well, the optimal prediction of xn plus L is going to be solution to an optimization equation. So we have xt. We suppose that it is stationary. It has mean mu, which is known. It has autocovariance function gamma x, which is known. And we wish to forecast x n plus 1 plus L for some L, starting at 0, given the sample x1 to xn. So this gives us what? It gives us a function of x1 to xn which we wish to estimate. So how do we estimate in an optimal way? Well, the answer is given by the projection theorem. There exists a unique projection of xn plus 1 onto the space of all random variables generated by x1 to xn, which will minimize the error when the error is measured in terms of the mean square. Okay, does that mean that the problem is finished? Well, the answer is no, because such a thing here is just something called a conditional expectation. And I don't know if do you have a course on non-parametric statistics? You probably do. So you know all these kernel estimators and so on, but so you know that estimating a conditional expectation is well, it's hopelessly difficult. It's a very, very difficult problem, even with modern computers, and even in 2020. Estimating something like this without making simplifying assumptions is impossible. So here in time series we choose to simplify the problem by projection, rather than projecting on all measurable functions of a random vector, we project onto all measurable functions which are of a certain form, and the form we are interested in are the random variables which are linear combinations of the x1s plus a constant. So rather than projecting on the space of all functions which are measurable in x1 to xn, we project on all functions which are of this form. And when we have this, well, it is possible to obtain, I put explicit-ish because they're not really explicit, but it's possible to do things, at least numerically, to get solutions to the optimization problem here. And we have already done, well, you have already done some versions of this in the exercises. Okay? So, to continue, well, let's imagine that we are trying to predict xn plus 1 plus L. I'll remind you of the notation. L is larger than 0. L is this. So you have observed from 1 to f. You have observed x1 to xn, and you put yourself at the time horizon xn plus 1 plus L, and you want to project this guy given these guys? Well, your projection will be a certain combination of the x1 to xn with certain coefficients, which I will denote alpha n0 of L up to alpha n of L. So something like this. And we already noticed that the optimal projection in terms of the scalar product on L2 will just be given by the coefficients which solve this orthogonality condition for all elements of the linear span of 1 to xn. And we also already know that this is equivalent to the system of equations which is here. So we want our projection here to be orthogonal to 1, that's the equation here. It has to be orthogonal to x1, that's the equation here for k is equal to n. It has to be orthogonal to x2, x3 up to xn, so it gives us this system of equations, which we've already written at least 10 times during this course. So in other words, if I just spell out these equations, what I need to do is solve this system of equations here. So I have to find the coefficients alpha n0 to alpha nn, which solve this. And now, as we already know, we make the assumption of stationarity, and with this assumption of stationarity, well, this equation here, xn plus 1 scalar product 1 is just the mean of xn plus 1 plus L, and that's stationary, so that's just mu. Alpha n0 stays, and this gives us just mu times the sum here, so it gives us this equation here. Is everybody okay? So you don't have to react. I'll just give you a few seconds to react. Is everybody okay with this equation here? Yes. Now here we know that this is equal to this plus this. Sorry, this is equal to this minus this because of this equation. So we plug that in here, we develop the equation, and we get all the combinations of these guys with these guys, which will give us that it will give us this system of equations, well, these equations here. So we have expectation of xn plus 1 plus L times, well, minus mu. I take one of these mu's here. Minus mu here times xn plus 1 minus k. So this is the first term. And the second term comes from this sum here, which I plug in here, and I have a mu which comes out. And then I will get this equation here. So I'll let you do the details, but do you see how to get to this equation here? Well, maybe you can do it. Is it really worth it? I guess it's not worth it. I mean, you just replace this by this, and then you simplify on either side, and you would get this equation here. And now we finish up by saying that all these products here are covariances. These are covariances, and therefore we have the covariance at lag by stationarity, covariance at lag L plus K is equal to a certain combination of the covariances at lags K plus K minus J. Yeah, L plus K minus J, like this. And of course the first equation we just rewrite it here. So I know you have to work it out slowly, but do you all see how to get here? I guess that's a yes. So now this thing here is what? Well, that's a triangular, maybe I should do some notes. So this thing here, which I will call star, is a triangular array of equations, which might help out to write out in detail. So it's, what is it? It's alpha n0 of L is this. And this, and And now let's imagine that I take n, I'll take L is equal to 0 just for the sake of illustration. I take n is equal to 1. What do I get? So here we have n equations. This is k going from 1 to n. So if L is equal to 0 and n is equal to 1, I will get alpha 1 0 of 0 is supposed to be equal to mu times 1 minus alpha 1 of 0. And then the second equation is what? It's gamma of 1. So k is equal to 1, so 1 plus 0 is 1. Gamma of 1 is supposed to be equal to alpha alpha 1 of 0 times gamma of 0. And now this is easy to solve. I mean, we get what? We get alpha 1 0. We get alpha 1 1 of 0 is just gamma, so it's just rho of 1. And we get alpha 1 0 of 0, which is just mu times 1 minus rho of 1. Okay? Now if n is equal to 2, so I won't do them all, don't worry. I'll just do the first two. Then we get what? We get alpha 2 0 of 0 is this. And then we get alpha 2 1 of 0, sorry, gamma of 1 is alpha 2 1 of 0 times gamma of 0 plus alpha 2 2 of 0 times gamma of 1. Gamma of 2 is equal to alpha 2 1 of 0 times gamma of 1 plus alpha 2 2 of 0 times gamma of 0. And again, now we have three equations in three unknowns, the unknowns being this guy, and this guy, and then the knowns being this, and this. And well, again, I mean, this time I'm not going to do it, but you can extract alpha 2 1, alpha 2 2, and alpha 2 0. As functions of gamma 1, gamma 2, and gamma 0. Okay, so when you go to n is equal to n, say, then you have n equations in n unknowns. So this gives us a triangular system of equations. And if we just rewrite this, again, I go back to n is equal to 2 because that's quite nice. So what do we have? Our unknowns are what? Well, it's gamma, sorry, it's alpha 2 1 of 0 times alpha 2 2 of 0, as I put that as a vector, is supposed to be equal to gamma of 0, gamma of 1. Oh, sorry, I'm not doing this correctly. So if I just write these two equations here in matrix form, I get this. So my unknown alpha, what I'm going to call alpha n, is given by it's a solution to a matrix problem. I'll call this gamma 2. Sorry, I'll call this alpha 2, and this I will call well, gamma 2 of 0. Yeah, and this I will call gamma n, gamma 2. So what we see is that these guys are solution to the matrix equation which I can rewrite gamma 2 of 0 is equal to capital gamma 2. I'll put a double bar here to indicate the matrix, here to indicate a vector, times alpha 2 of 0, and then the first equation just stays what it is. Okay, so now I've rewritten my system of equations. So this gives me the equation, let's say dot, and this gives me, sorry, it's the other way around. This gives me that equation here, and this gives me this equation here. Everybody's following? So, well, we've done this many times already, and we'll do it again once more, probably today, if all goes well. All the mystery of our system of projections is contained in this equation here. So once again, the important objects for our estimation purposes, well, here it's projection, but it's still a form of estimation. The important objects are what? Well, it's this matrix of covariances and this vector of covariances. These are the guys which will govern everything. So everything is hidden in this this equation system. So far so good. Okay. Well, the really important part is this guy, because typically we will be supposing that the mean is 0. So in fact this will go away, because if we suppose that the mean is 0, then we just have 0 on the left hand side. So the really important part is going to be this system of equations. If the matrix, so it's a square matrix, if the matrix is not invertible, so if its determinant is 0, then your system of equations will have no unique solution, but all solutions will result in the same projection, but it's not going to be unique. If gamma n is invertible, then we can write this. So alpha n of L is simply the inverse of gamma n applied to gamma n of L. And we can even compute the intrinsic variance of this guy. So the mean square prediction error, which is the variance of the projection. So the variance of the projection is the variance of this guy. That by definition is the L2 norm of the difference. And now to compute this L2 norm, I just take the scalar product of this guy with himself, and this gives us the scalar product here with this, minus the scalar product of the guy with the other side. So it's the scalar product of himself, of this guy with himself. So I get these two terms. By definition, he is orthogonal to anything which is a linear combination of the x1s to xn's. So by definition of the projection, this guy goes away, and I'm left with this thing here. And that's what? Well, that's the variance of xn plus 1 plus L with himself, which is just gamma of 0. And then I'm left with the scalar products of xn plus 1 plus L with this guy. And well, I know that xn plus 1 plus L is a linear combination of, oops, there's a typo here. There's an alpha n e I of L, there's an L missing. So I just write out what he is. And I will be left with I'll be left with well, in fact what I should do here is I should subtract the mu, and I should subtract the mu here. That way it works correctly. And then I'll be left with this linear combination here, which just gives me the combination of the alpha n's with the covariances. That's just the covariance at lag L minus I. Sorry, L plus I. And then if I just write this out as a vector, well, that's this guy as a line vector, multiplied by this guy as a column vector. So if I maybe write it out again properly, it's alpha n 1 of L to alpha n of L multiplied by gamma n of 1 multiplied by gamma. So what's my vector gamma? Like this. So it's like this. So this guy here is equal to this guy here, which is equal to this guy here. And now what do I do? Well, I simply replace alpha n, this guy, by what he is, and alpha n is this guy if there's a solution. So the transpose of gamma n minus 1 times gamma n is just going to be equal to this guy. Okay with this? So it's computations that should not be too mysterious. And then we're left with the quantity that will play a role. So I'll give it a name. I'll call this nu n of L. So the mean square prediction error at lag L is given by, well, this pretty quantity here, or which I call nu n of L. And the optimal prediction is given by these guys here. Okay, now...
Sorry, are we under the assumption here that the mu is 0 because we go from the scalar product, the inner product to the covariance?
No, that's why you have to subtract here mu on either side. And then you have the covariance.
Okay.
Okay, so I'm slightly cheating here. Well, I'm not actually, but so if you subtract here the mean mu, then you have this times this, that gives you the covariance, and then this times this gives you the covariance. So it should be minus mu here, sorry, like that.
Okay, yeah, thank you.
Okay? Okay. Now, important question is when will this be the case? Well, the answer is well, as with the rest of all this, the answer is astonishingly simple. So if you have a stationary process with a covariance function gamma x, if the variance, so on the diagonal you have something which is strictly positive, and if your gamma x's of h go to 0 as h goes to infinity, so if you have a function here which goes to 0 as h goes large, then necessarily this matrix here, so this square matrix, so all these square matrices, gamma, so this 2 by 2, 3 by 3, 4 by 4, and so on, all these guys will be non-singular. So again, this is crazy. I mean, all you have to check is that your variance is non-zero. Well, that's if that's not the case, then your system makes no sense. And you have to check that you have a system of that your covariances go to 0 as h grows large, and then you're guaranteed that all these matrices here will have a non-zero determinant. And how'd you do that? Well, yeah, you're just using properties of symmetric matrices to show that it works. I'm going to skip this proof. You're more than welcome to read it. But basically, you just start by the fact that by assumption gamma of 0 is positive, and then you imagine that it could be singular at some point, and if it could be singular, then you would arrive at some form of contradiction with the fact that you're actually looking at a covariance. So yeah, so to make a long story short, that's all you have. So because you have the variance which is positive, then this special structure of matrix guarantees that you cannot have a determinant which would be 0 at any later stage, because if it could be 0, then it would imply that gamma of 0 should be 0, and that's what we do in the proof. but I'm going to skip this to save some time. And yeah, I don't think I'll need it in the sequel, so I'm allowed to skip it. So if we summarize what we've just said, if you have a stationary process with mean mu and autocovariance function gamma x, so this should be ACVF, which has a non-zero diagonal, and such that the covariance goes to 0. This should be a H. It would be nicer with a H. The covariance tends to 0. So that is the case of the moving average processes, and that's because we saw that the autocovariance of a moving average was something, 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 and then drops to 0. So as the H grows large, the autocovariance of a moving average does go to 0, whatever the order. And it's also the case of our autoregressive of order 1 and even of order 2, for those of you who did the computations. You see that it oscillates, but it goes to 0. At least order 1, it was phi 1 to the power h over 1 minus phi 1, and that, because phi 1 is less than 1, it goes nicely to 0, or it oscillates to 0. So for the AR1 and the MAQ, this is satisfied. And under this very, very, very simple assumption, then, well, basically you're allowed to do optimal prediction. Your optimal prediction is given by this quantity here. And the coefficients in your optimal prediction are, well, yeah, maybe I should put a hat here, it would be prettier. And your predictions are given by, no, I'm not going to put a hat. I know why there's no hat. Let's leave it like that. And so your coefficients are given by as solutions to this system of equations here, and the mean square error of this prediction is given by this expression here. So could I imagine an exam type exercise here? Yeah, so we could imagine a question of the style show, prove proposition 4.2 by giving all details, giving all details at every step, and then I would give you a hint or help. You are allowed to use proposition lemma 4.1 without proof. So what? So I mean, I don't know if that's a clear question. So that would be the type of question that I probably will be asking you. So here you have to give all the details. So you have to say, well, proposition 4.2, it says all this, and then you have to say, well, then yes, this is indeed the optimal prediction by showing that it satisfies the prediction equations, and then you have to justify that you can invert the solution because this suffices to apply lemma 4.1. And then you have to do all the computations, including the computations that I stepped over here. And so you're expected to hand in a very detailed and clear explanation. Is that more or less? Do you understand what I'm expecting from you when I ask you something like this? So the easy version is, of course, to copy the course. And if you copy the course, well, I guess if the question is out of 6, you'd get already 3, because I mean, everything is already here. But if the more details you give, the more happy I will be. Okay. So, crucially for us, the condition holds true for all stationary and all causal. The condition holds true for all stationary and causal ARMA processes. That means that all stationary and causal ARMA processes have a covariance which is positive, have a variance which is positive, and which the covariance goes to 0 as h goes to infinity. Now, in the sequel, I will concentrate exclusively on the case L is equal to 0. So when L is equal to 0, this is basically the most important. So if L is equal to 0, so the notations are a bit annoying. So the idea is that we have x1, x2, xn minus 1, xn, and given these guys, we just want to predict xn plus 1. And that's the case L is equal to 0. Okay. So, for the notations, I will now use alpha n to denote alpha n of 0, and gamma n to denote gamma n of 0, and nu n to denote nu n of 0. So it's what I had here. So alpha n's, these alpha n's are sequences. When n is equal to 1, we have 2 guys. When n is equal to 2, we have 3 guys. When n is equal to 3, we have 4 guys. So these are sequences which are increasing in increasing dimension. Same thing for the gamma n's. Gamma n is where is he? Gamma n is therefore gamma n of 0, so it's gamma of 1 up to gamma of n. It's an increasing, as n grows, we have an increasing vector, and these matrices here, well, they don't change; they stay the same. Okay. Now let's have a look at what it gives on an example. So we start with the simplest example, which is an AR1 process. Now, consider the AR1 process with some parameter phi1, which is supposed to be less than 1 so that everything, only nice things happen. We take white noise sequence with variance sigma squared. The mean is 0. We've already computed the covariance function. We know that the covariance function is of this form. Therefore, the equations become like this. Yeah, well, actually, here I take it, so I'm immediately contradicting myself with. So yeah, here it's no problem to take general L, but yeah. So here it's no problem to keep L as L general, but for the next processes it won't be possible. So we keep L general, and our system of equations become this is equal to this times this. So this does not depend on L. This has a nice dependence on L, because you have phi1 L everywhere, and we have alpha n1 to alpha nn of L. Now this matrix here is invertible. There's only one solution, and as is often the case, if you're smart, you're faster than if you're not smart. So here, well, either you can try to invert this thing and get something, or you just look. Maybe let's look at an easy case. We take n is equal to 2. So we have phi1 to the power L, phi1 to the power L plus 2, which should be equal to 1 phi1, phi1, 1 times something and something else. So this gives us what? Well, we see that we have alpha 2 1 of L plus phi 1 alpha 2 2 of L. We have phi 1 alpha 2 1 of L plus alpha 2 2 of L. And it's not really hard to see that if we take alpha 2 1 of L to be phi 1 to the power L plus 1, that should be good. and alpha 2 of L to be 0. If we do this, we're happy, because then we have this is the same as this, and this is the same as that. That goes away, that goes away. And because the solution is unique, we know that we have the solution. Okay? Now in general, if for general n, well, the same argument applies. We just need the first column. So here we need a phi 1 to the power L plus 1. Phi 1 to the power L plus 1 will give us phi and so on. So if we just take the first guy to be this, and all the other guys to be 0, we're finished. Okay? Okay. Yeah, but that's good, because 14 says, well, xn plus 1 hat is alpha n 0. Well, that's just 0 plus the sum of the alpha n i's, but all these guys are 0 except the first one. So we have this lovely equation here. So for quite cheap, we have just seen that given x1 to xn, the optimal prediction in an AR1 model, the optimal prediction is just this guy. Yeah, but that means that, as could be expected, of course, because an AR1 model is very, very simple, the forecast just depends on the last observation, and the coefficient does not depend on n. It only depends on the value of the lag at which you want to make your forecast. So all previous observations can be disregarded. They cannot improve the forecast further. In other words, all the useful information about xn plus L is in the entirely all the useful information about this guy in the whole process is just contained in the last implementation of the process. But again, it's not surprising. I mean, our guy here, don't forget, it's just this guy. So, of course, xn plus 1 only, I mean, there's nothing surprising. Xn plus 1 only depends on xn plus some independent noise. So there's no surprise here. If we look at the variance of the prediction error, we just compute it, and we will get this expression here. When L is equal to 0, it gives us sigma squared, and when L goes to infinity, it gives us 1 over 1 minus phi 1 squared sigma squared, and this is exactly the unconditional variance of xn. And last but not least, the variance is an increasing function of L, but that's obvious because the further you go from xn, the further you go this way, the further the uncertainty is going to be. Because of course, you can perhaps project quite precisely at lag 1, but you cannot project precisely at lags at higher lags. I mean, your projections will become more and more volatile. Okay, so far? Okay. Now, let's have a look at ARP. And here it will become a bit ugly, so I'll fix my discussion to the case L is equal to 0. So an ARP model is of this form. Simply by doing the same thing as usual, we can see that the autocovariances satisfy a pth ordered difference equation. So there will be two possibilities. If you're so let's maybe make a little drawing again. We have x1, x2, x3, and so on, xn. And we want to look at xn plus 1. Well, there's two situations. Either you're working after p. So if p is here, then you've already observed everything you could observe, and you're moving forward in the process when you've already seen. So xt depends on the p previous observations. So if you're working after time p, you've already observed everything that could be observed, and you're not gaining more information. Whereas if you're working after time p, sorry, if you're working before time p, well then the situation is a bit different, because you have xn will depend on observations that have not been made yet. So you do not have the same system if you're working at n before p or after p. Is that clear? Okay. Well, if n is larger than p, well, I quite like this. So you could work. I mean, you could work it out. You can do all the equations and everything. But if you think about it, xn plus 1 is already a linear combination of x1 to xn. But by definition of the model, xn plus 1 is already a linear combination of the p previous guys plus some error. So let's say educated guesswork tells you that the only natural thing to do is to look at this as your linear combination of the past to predict the future. Does that sound reasonable? And well, I like saying that when it's pretty, it's correct. That's not always true, but here it is. So you get this, and then you check that this is indeed the correct forecast by showing that it satisfies the equations, and everything works nicely. You could also invert the system and solve, and then you would get the same answer. It would take you much more time, but you could also do it, and you would get the same answer. So this gives us the optimal prediction at lag 1, and if n is less than... So, sorry, I'm forgetting something. So our coefficients are what? Well, that's important here. This equation here is very important. I was going to skip over it. This equation will play a crucial role in the second part of this class. So what does it tell us? It tells us that so if n is larger than p, we know that x hat n plus 1 is going to be what? It's going to be phi 1 times xn plus so on plus phi p times xn minus p plus 1. Let's take an example just to make sure. I take p is equal to 4. So it tells us what? It tells us x hat n plus 1. And take p is equal to 3. It's easier to write. Okay, and this is my alpha n 1. This is my alpha. So let's not forget that we are trying to find we are trying to find coefficients for which we can write x hat n plus 1 as a linear combination of all previous elements in the past of the process. So x1 to xn. And now here we see that we have something which only depends on xn, xn minus 1, xn n minus 2. So it tells us what this equation, it tells us that the alpha n1 is phi 1, alpha n2 is phi 2, alpha n3 is phi 3, and all the alpha nj's for j larger than 4 are 0. So remember when we were talking about the autocorrelation function? The autocorrelation function of a moving average process was something, 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 poof, goes to 0. And here now we have that these coefficients in the prediction of the element at lag 1 of xn in terms of x1 to xn, the optimal coefficients in here are something, 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 then 0 for all lag superior. So this is for an AR3 model. That's going to play a role in the sequel. But now this equation 16 tells us that we have these coefficients explicitly. They're here. If n is less than p, I let you read this up. It's a bit more complicated. Well, it's not more complicated. It's a bit more messy. I'll let you do it. We could work out the forecasting equations for L larger than 1. This can be done recursively. Yeah. We don't have the time. We only have 24 hours to teach all this. It's not worth going into details. It would be a very good exam question again. Because, I mean, here we have something very clear. So for example, a good exam question would be: show this equation here. Show that the prediction at lag 2 is given by these coefficients here. Now all the details are available in the book by Nurser, which you have, and it's in section 3.1.1. So that's a kind of question again that can be asked to students like you who will be working from home with your computers and everything. So far, so good. Okay. Now things are. So I'll do this example 4.7, and then we'll have a break. Intriguingly enough, things are much more complicated with a moving average process. So when we have a moving average process, the model is of this form, and we have already computed the autocovariance function, and it's given by this thing here. For example, you can go and see example 3.18. Now, again, do not trust me on this. Write it out yourselves. Write out the equations, but you should be able to see that. So I'm working with a moving average of order 1, while then gamma of 1, gamma of 2, and so on. It's just theta 1, then 0, 0, 0, 0, 0 is supposed to be equal to the. So on the diagonal we have all these terms here, which come from here. Sorry, yeah, the sigma squares do not play a role, they cancel out. And then off diagonal we have theta 1, and so on. So this is a very simple equation in a sense that gives you the expression of the alpha n's in terms of the thetas. Despite the fact that this equation is very simple, these matrices have a very simple structure, it turns out that the forecasting function of the moving average of order 1 will not be like here. So here it only depended on one previous observation. Here it will depend on all previous observations. So to forecast at lag n plus 1, you need xn up to x1. There's yeah. Again, here, as before, it would be possible and instructive to consider higher values, but this is too annoying to detail here. Again, also, all this is already implemented in software, so you don't really need to suffer the details. It's already implemented. Now, let's have a look at a numerical example to see what's happening. So, I take a moving average process, variance 1, and I take theta 1 to be minus 0.9. We start the exercise in period 0, so we have observed, what's the exercise? We observe we observe nothing. If we start in period 0, we observe, where is it? We observe nothing, and we want to predict x1. Well, here, if we observe nothing and we want to predict x1, the best forecast in this case is just the unconditional mean. And the unconditional mean of the xi's, because it's a moving average of order 1, it's just 0. So your best prediction of x1 is 0. Okay, this is pretty trivial. The variance is therefore the variance of x1 minus 0, which is just the variance of a moving average model, which is sigma squared times 1 plus theta 1 squared, which I trust to be equal to 1.81. That's okay? Step 1 is okay? Well, step 0 is okay. Step 1. We have observed x1 and we want to forecast x2. Well, then the equation system becomes like this, and this gives us alpha 1 1, which is theta 1 over 1 plus theta 1 squared, which I can compute. I just replace this by this and I get this. The corresponding variance is easy to compute. I just look at the variance of x2 minus this guy and I get this quantity here. Now in period 2 I have observed x1 and x2 and I want to predict x3. The coefficients in the prediction now have to satisfy this system of equations here. And what do I see? I see that I have two coefficients, alpha 21 and alpha 22, which I order here. I can compute the mean square error, which is going to be given by this. So if I put this all in a table, so I think I'm taking all this from Neusser. I can't remember where I took it. I think it's from Neusser. But I did do all the computations. I suppose the R code is somewhere. But I'll let you do this anyway yourselves. So at time 0 I have nothing. There's nothing here. And I have my variances here. At time 1 I have one coefficient and that's my variance. At time 2 I have two coefficients and that's my variance. At time 3 I have three coefficients, and so on. And of course, as I go on, I will have an infinite series. So what we see is that in this simple moving average of order 1 situation, at any time n, the prediction of xn plus 1 depends on all the observations. None of the coefficients here are 0, so we depend on all the observations to predict optimally xn plus 1. We also see that we have a sequence of variances, and these variances decline monotonically to the limiting variance, which is supposed to be 1. Now, in this sequence of capital importance is, so what's happening? At time 1 you have your optimal prediction, and then you add an observation, poof, and then you want to recompute your thing to optimally predict again. And the importance of adding one observation to your system, so when you go from x1, so when you go from n equals 10 to n equals 11, all you're doing is adding x11. So you're just adding one observation, and then you recompute everything given this one observation. The influence of the addition of this one observation is measured in the last coefficient of the sequence. So it's the coefficient alpha n1, and alpha n1 here is this guy. Well, this guy measures the importance of adding new information to your model, and these terms are called partial autocorrelations, and they are very, very important for the modeling purpose. So they are the last missing ingredient. So for the moment we had means autocovariances, while we still needed partial autocovariances, and once we have these two, we are well, basically the course is finished. So I will go back on this after the break. Now, this is okay so far? You understand at least the idea behind the computations? So, can't remember, I must admit, but I think I get you to do this in the exercises. So you will do it anyway. And I will do the detail at some point, that I'm sure. But you should, you have to be able to do this. So you should work it out. Now, something we've already done is forecasting from an infinite past. We have seen that in this theoretical situation where we dispose of an infinite past, then the optimal prediction has already been dealt with. It's given by this guy. That's something we've already done. And this gives us the limiting case of this situation here. And you see here, none of the coefficients are 0. Even in the case of an infinite past, you will have an infinite sequence of coefficients which are non-zero. Now, just as a remark, which was something that will come into play later, If you remember, the solution to the autoregressive of order 1 was sum of the phi 1s to the power j times x n plus 1 minus j. It was some kind of geometric sequence here. And now what we see is that in the moving average, the optimal prediction is sum of the parameters to the power j times the past. So there seems to be some kind of dual version. So whatever the ACF is for the autoregressive process, the PACF will be for the moving averages. We will come back to this well, today already. Something that you should do is the same thing for ARMA 1.1. Again, that's typically exam question. Work this out. And the maths are the same as the maths that we've done here, except that the model is slightly different. You can certainly, I mean, if you Google prediction of ARMA 1.1 infinite past, you will get this solution somewhere correctly detailed. Voila, I think it's a good time to have a break. So let's have a 15-minute break. It's 3:20, 3:25. So we start again at 3:40. Okay? I will stop the video.